In this video, we're going to take a look at linear programming problems. Now, linear programming is a method of solving problems involving inequalities and more than one variable. Now, linear programming is widely used in fields such as finance, planning, manufacturing, and logistics to help minimize costs or maximize profits. And what we need to be able to do then is formulate a problem as a linear programming problem. So to begin with here, let's just break down then each part of a linear programming problem separately. So to get us started here, we have decision variables. Now, the decision variables in a linear programming problem are the numbers of each of the things that can be varied. So what do we mean by that? So for example, then the cost of a box of chocolate as well as the number of boxes produced here would be examples of decision variables. Now, the variables, which are normally just x, y, z, etc., will be the letters in our inequalities and also our objective function. As you can see here then, I put objective function in bold because this is the next thing that we need to learn about. So let's just take a quick look then at the objective function. So as we just said then, the next part of a linear programming problem that we need to learn about is what's called the objective function. So it helps to think about the objective function in two parts here. Now, the first part is the objective, which is the aim of the problem. Now, this may be to minimize costs or maximize profit. And this will be given alongside the objective function itself. Now, the second part is the objective function itself. And this is usually written as an equation in terms of the decision variable. So for example then, c is equal to x plus 3y, or p is equal to 2x plus 3y. So it might say then, minimize c is equal to x plus 3y, right? Minimize the cost here. Or maximize p equals 2x plus 3y. Maximize the profit here. So those are just two examples there of an objective function. Now, as we work through any linear programming problem, we also need to consider the constraints. Now, the constraints are the things that will prevent us making or using an infinite number of each of the variables. So examples of the constraints are the quantity of raw materials available, the time available, or the fact that we cannot have a negative quantity, etc. Right? You get the idea? I think in a practical sense, this should all seem quite intuitive. And each constraint will give rise to one inequality. And then finally, to finish with here, let's just learn about feasible solutions and also the feasible region. So to finish with here then, like we just said, right, let's just take a quick look at feasible solutions and also the feasible region. Now, if we can find values for the decision variables that satisfy each constraint, we have found a feasible solution. And for a graphical linear programming problem, the region that contains all the feasible solutions is what we call the feasible region. Now, the optimal solution is the feasible solution that meets the objective. And for some problems, there may be more than one optimal solution. So if we put this all together then to formulate a problem as a linear programming problem, we start by defining the decision variables, that is x, y, z, etc. We then state the objective, so that's either to minimize or maximize alongside an objective function. And then finally, we write the constraints as inequalities. So to finish with here then, let's just put all of this together and work through an example. Let's just get started then with this practice question here. Now, as we can see then for this question here, there's quite a bit going on and it is a little bit waffly. Not that waffly is an adjective, but there we go. I'm going to use it anyway. Why not? So, like I said, quite a lot going on. So before we do anything else, let's just quickly read through the question. Okay. So what we're told here then is a coffee company produces 3 different blends of coffee. So we've got morning blend, afternoon blend, and evening blend. The coffee must be processed, blended, and then packed for distribution. And the table below here also shows the time taken in hours for each stage of the production of a ton of coffee. And the table also shows the profit in hundreds of pounds on each ton. It then says here that the total times available each week for processing, blending, and packing are 32, 24, and 26 hours respectively. And the coffee company wishes to maximize their weekly profit, which intuitively should make sense, right, in the context of running a business. It also says here, let X, Y, and Z be the number of tons of morning, afternoon, and evening blend produced each week. So for this question here then, all we actually want to do is just formulate the situation above as a linear programming problem, clearly stating the objective function and the constraints as inequalities. Right, so to begin with here then, generally speaking, formulating linear programming problems can be not difficult as such, but there can be quite a bit going on. This question here is actually a little bit more straightforward because in the context of this question here, we only really have one constraint. And that constraint then is the total times available for processing, blending, and packing each week, right? So to begin with here, we always start with the objective function. So for the objective function here, so objective, what we want to do here then, as the question mentioned then, is maximize their weekly profit. So what we want to do here then is maximize P. So my objective here then is to maximize P. Okay, so maximize P here. And that would be equal to, so based on the table here, as we can see then profit is this column, right? So for morning blend, that is X here, as we're told. For afternoon blend, that is Y. And then for evening blend, that is Z. So to maximize P here, that would be equal to 3X plus 4Y plus 5Z. So hopefully, nice and straightforward there, just to get us started with the objective function. So we get 3X plus 4Y plus 5Z. Okay, so to begin with there, that is our objective function. Good stuff. And what we now need here then is the constraints, right, as inequalities. So this will be subject to. So subject to. What I now need to do here then is present the inequalities for this linear programming problem. So as we mentioned before then, the only constraint here is the total times available each week for processing, blending, and packing. Okay, so in that case, and what I'm going to do here is go down each column, right? Processing, blending, and packing, because these here then are the constraints that we're looking at. So for my first inequality here, similar to what we did with the objective function here, right, when we were maximizing P, I'm going to get 4x plus 3y plus 2z. So subject to then 4x plus 3y plus 2z. And now for the inequality here, this needs to be less than or equal to, so less than or equal to the time here for processing, which is 32 hours. So 4x plus 3y plus 2z is less than or equal to 32. Perfect. So for the next one here, this would be for blending. I'm going to get 2x plus 2y plus 3z. So 2x plus 2y plus 3z. And again, this must be less than or equal to. So this must be less than or equal to, what is the time constraint here? 24 hours. So this is less than or equal to 24 there. Perfect. Okay. And now for the final inequality here then, what do we get? So going down the packing column here then, I get 3x plus 4y plus 2z. So 3x plus 4y plus 2z is, again, less than or equal to, so we're less than or equal to the time constraint here, which is 26 hours. Okay, perfect. The only thing remaining here then is the non-negativity constraint, right? So in the context of this question here, clearly x, y, and z, given that x, y, and z represent a quantity here, the number of tons of morning, afternoon, and evening blend produced each week, clearly that can't be negative, right? So in that case then, x, y, and z here must also be greater than or equal to 0, okay? And there we have it then. So what we've done here is took this situation, the context of this question here, and formulated that as a linear programming problem. And that's always the first step, right, in any linear programming problem, if that's not already done for us. Now, as I mentioned before, right, this question here was a little bit more straightforward. So what I'm going to do here then for the next video, the next members video anyway, is take a look at a slightly more complicated example, right, where we're formulating something a little bit more complicated in general, okay? So there we have it then. That gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on linear programming problems.